If you thought the latest images from the James Webb Space Telescope were impressive, what you're about to see will completely change your perspective. A new space telescope has quietly begun sending back images so detailed, so vast, and so revealing that scientists openly admit they were not prepared for what they were seeing. The Euclid Space Telescope has just released its first light images, and they do far more than showcase beautiful galaxies. They reveal structures we barely understand, patterns shaped by invisible forces, and a universe that appears far more complex and unsettling than anyone expected. Tonight, we'll explore what Euclid has captured, why astronomers are calling these images revolutionary, and why some of them become genuinely terrifying once you understand what you're looking at. Stay with me until the end, because this is only the beginning of what Euclid is about to reveal. Euclid is not an ordinary space telescope. It was never designed to focus on a single nebula or zoom in on one spectacular galaxy. Its mission is far more ambitious and far more unsettling. Launched by the European Space Agency in July 2023 and positioned approximately 1.5 million kilometers from Earth at the second Lagrange point, L2, Euclid was built to map the universe on a scale humanity has never attempted before. Its ultra-wide field of view allows it to capture enormous portions of the sky in a single observation, while maintaining remarkable resolution. This means Euclid can clearly image individual galaxies, while simultaneously revealing how millions of them connect into immense cosmic structures. What makes this especially fascinating is that Euclid is not simply mapping visible light. It is mapping the influence of dark matter itself by measuring the subtle distortions in galaxy shapes caused by gravitational lensing. In other words, Euclid is revealing the hidden skeleton of the universe, a structure shaped by something we cannot see and still do not fully understand. When Euclid returned its first mosaic of the southern sky, scientists were astonished by the sheer scale of what they were seeing. During a relatively short observing period, the telescope captured 260 individual images covering an area of sky roughly 500 times larger than the full moon. When stitched together, these observations revealed millions of stars and galaxies. Yet this enormous image represents only about 1% of the complete cosmic map Euclid is expected to produce. That realization alone is staggering. What we are seeing is not a finished picture, but merely a fragment of something almost unimaginably larger. Researchers can zoom from the largest cosmic structures down to individual galaxies without sacrificing clarity, revealing how matter is organized across immense distances. This mosaic is far more than a beautiful photograph. It is a preview of the largest and most detailed three-dimensional map of the universe humanity has ever attempted, raising profound questions about how little of the cosmos we have truly explored. One of the most remarkable discoveries from Euclid's first images comes from the Perseus cluster, located approximately 240 million light-years from Earth. A single image reveals more than 1,000 known galaxies along with over 100,000 distant background galaxies. But the greatest surprise came when scientists examined the data more closely. Euclid identified more than 630 previously unknown dwarf galaxies hidden within the cluster, objects so faint they had escaped detection until now. This discovery is important because dwarf galaxies are extremely sensitive to the gravitational influence of dark matter. Their shapes, positions, and distortions act as traces, helping astronomers determine where dark matter is concentrated. The fact that so many of these galaxies remained invisible until Euclid observed them suggests that dark matter's influence may be even more intricate than previously believed. The universe does not merely contain dark matter, it appears to be fundamentally structured by it. Euclid's images are reshaping our understanding not only of large-scale cosmic structure, but also of the smaller details within galaxies. In galaxies such as NGC 6822, Euclid revealed low metallicity stars whose properties resemble conditions in the early universe, offering valuable insights into how galaxies evolved billions of years ago. Within globular clusters such as NGC 6397, the telescope resolved faint stars on the outskirts that had previously been hidden by brighter neighbors, providing new clues about the history of the Milky Way. In regions like the Horsehead Nebula, Euclid's remarkable sensitivity uncovered evidence of free-floating planets and Jupiter-mass objects drifting through space without parent stars, suggesting that rogue planets may be far more common than previously imagined. Together, these observations paint a picture of a universe that is not calm or orderly, but dynamic, crowded, and constantly reshaped by both visible and invisible forces. As scientists combined more of Euclid's observations, a striking pattern became impossible to ignore. Galaxies are not scattered randomly throughout space. Instead, they are arranged along enormous filaments, vast cosmic threads stretching across hundreds of millions of light-years and intersecting at dense nodes where galaxy clusters form. Euclid's images make this structure clearer than ever before. The universe begins to resemble an immense interconnected network, with matter flowing along invisible pathways shaped primarily by dark matter. These filaments are no longer just theoretical concepts. Their influence can be seen directly in the way galaxies bend, stretch, and align with one another. The most astonishing aspect is not simply that they exist, but the incredible scale on which they dominate the cosmos. Every galaxy, every cluster, and every enormous cosmic void exists within this vast web, guided by forces that scientists still cannot observe directly. One of Euclid's most remarkable capabilities is its extraordinary precision in measuring gravitational lensing.